Electronic components can be connected in a variety of configurations to form functional electrical circuits. The two simplest types of circuits are the series circuit and the parallel circuit. A circuit is said to be in series if all of its elements are connected along a single path with the current flowing in the same direction through each component. For instance, if the source current in a series circuit is 5 amps, then no matter where along the circuit you take an ammeter reading, it will also register 5 amps. Although current is constant throughout a series circuit, voltage is not. Voltage in a series circuit is divided across the load resistors so that the sum of the individual voltages equals the total voltage applied. This relationship is known as Kirchhoff's law. By adding the voltage drop across resistors 1, 2, and 3, you can determine the total voltage applied at the source. In this case, the total voltage is 5 volts plus 4 volts plus 3 volts, or 12 volts total voltage. The second basic circuit form is known as the parallel circuit. Like a series circuit, the parallel circuit has multiple components or loads. However, in a parallel circuit, the current has multiple paths along which to travel. Each of these paths is known as a branch. An important difference between a series and a parallel circuit is that the voltage in the parallel circuit is the same across all branches. The current along each branch will vary, but when added together, these various branch currents will equal the current at the source. For example, look at these ammeter readings at the various branches and junctions of a parallel circuit with a source current of 10 amps. As the 10 amp current travels away from the source, it splits at junction 1 into two branches that have currents of 2 amps and 8 amps. The circuit branches again at junction 2, and the 8 amp current splits into 3 amps and 5 amps. As the current returns through junction 3, the 3 amp and 5 amp values recombine to give an amp value of 8. At junction 4, the 2 amps and 8 amps currents recombine to equal the 10 amps of the original source current. An important difference in a parallel circuit is that voltage is the same throughout the circuit, so using a voltmeter to measure volts at each load will yield voltage readings equal to that at the source. Total resistance in series and parallel circuits can be determined using basic equations. The total resistance of load resistors, R1, R2, and R3, shown here in series, can be determined by simply adding their ohms values together. So, if R1 has a resistance of 20 ohms, R2 a resistance of 30 ohms, and R3 a resistance of 10 ohms, the total resistance of the circuit is 60 ohms. Calculating the total resistance of resistors in a parallel circuit requires the use of the product over sum equation. In this parallel circuit, if R1 is 50 and R2 is 80, then the combined or equivalent resistance of the two resistors would be 50 times 80, or 4,000 divided by 130, which is 30.7 ohms. Determining the resistance of a more complex series parallel circuit requires reducing the overall circuit and adding together all the combined resistance values. In this more complex series parallel circuit example, let's begin by combining the resistance of the two resistors farthest from the source, R3 and R5. Since these resistors are in series, we can simply add their values, 50 ohms plus 30 ohms, to get 80 ohms. Now, the R4 resistor and the equivalent resistance of the R3 and the R5 resistors are in parallel. Their combined resistance can be calculated by dividing their product by their sum. Thus, using the product over sum equation, we have 80 times 80 equals 6,400 divided by 80 plus 80, which is 160, giving 40 ohms. Now we have further reduced the circuit to two resistors in series, R2, and the equivalent resistance of the R3, R4, and R5 resistors. Again, because we have resistors in series, we can simply add the 60 ohms to the 40 ohms to get a combined value of 100 ohms. And finally, we are left with two resistance values in parallel, the R1 resistance of 200 ohms and the equivalent value of 100 ohms for resistors 2, 3, 4, and 5. Again, using the product over sum equation, we can determine the combined resistance. Multiplying 200 times 100 gives 20,000, divided by 200 plus 100, which is 300, resulting in an overall circuit resistance value of 66.67 ohms.